Hello everyone, this is Dr. Hopkins narrating the next video in our series. We're going to finish up our discussion of phase changes by looking at their dependence on changes in pressure and temperature. Alright, so we're going to start with maybe the most complicated of the three that we're going to discuss in terms of pressure-temperature dependence, and that's fusion or melting. So we'll start with the Clapeyron equation, which we introduced last time. And it relates dP dt, and we have delta S of fusion, so liquid minus solid, and then delta V molar of fusion, liquid minus solid. And then we're going to, based on our definitions of the entropy, we know that entropy of a phase change is the enthalpy of the phase change divided by the phase transition temperature. And that's Trouton's rule. So we're going to take this simple, the Clapeyron equation as a first order differential equation. We're going to split the variables, and then we're going to substitute in Trouton's rule in so that we have dP on one side, we have delta H of fusion and delta V of fusion, dt over T. Now if we want to solve this, we just need to integrate over our pressure ranges that we're interested in and our temperature ranges we're interested in. We're going to go ahead and make the assumption that delta H and delta V are constant over our temperature change, so the change in the actual melting point. Usually these kinds of changes are pretty small, so most of the time this assumption is not a bad one. So we're pulling that out, and so we would integrate this and we end up with the natural log of our melting points times the delta H of the fusion over delta V of fusion, and that would be delta P. And so what this says is basically what we found out from our phase diagram, from our chemical potentials. Now we know that the delta H, so the numerator here, is greater than 0. That has to be positive, and that's for all substances. So the heat of fusion is always positive. The molar volume change for fusion for most substances is greater than 0. So this is positive. So that means that in that case, the melting point would increase as we increase the pressure. Okay. And the one exception, well, there's probably more than one exception, but one notable exception is water. And water is one where the delta V of fusion is less than 0. And so in that case, the melting point is going to decrease as we increase the pressure on solid. All right, so then we're going to talk about the next phase transition, so vaporization. And then we start with, once again, our Clapeyron equation and substitute in the Trouton's rule. Okay, now in this case, we have something makes this much easier, actually. So the change in the molar volume is the gas minus the liquid. Well, you know, a gas expands to fill the container, whereas the liquid does not. So it's generally much, much larger than the molar volume of a liquid. So we're just going to assume that delta V is just the molar volume of a gas. And then we're going to assume that it's going to behave ideally. So we're going to substitute in RT over P for our molar volume. And let's check if this is a good assumption. In this case, what we're talking about is the vapor pressure above a liquid. Okay, so generally those are going to be pretty low pressures. When we have low pressure, we tend to have gases that behave like ideal gases. So it's not a bad assumption. And then we will substitute in to our top equation here. So this gets a special name. It's called the Clausius-Clapeyron equation. And actually the last equation that we derive is typically the form of the Clausius-Clapeyron equation you'll see. So then we have our differential equation. We need to split our variables. In this case, it's dP over P. And then we put the dt on the other side, which is dt over T squared. Right? We're going to go ahead and assume that delta H of vaporization is independent of temperature in this temperature range. And so we end up with this natural log of P versus this 1 over T relationship in terms of the vapor pressure above a liquid. So using the Clausius-Clapeyron equation, if we were able to collect vapor pressures versus temperature data, we can actually plot the natural log of that pressure versus 1 over T, and we should get a linear plot, and the slope will give us the delta H of vaporization, so the enthalpy of vaporization over R. So we can determine from this data, we can determine the enthalpy of vaporization of a particular liquid without ever actually boiling the liquid itself. Okay, and vice versa, we can take the Clausius-Clapeyron equation and use it to calculate vapor pressure. So if we knew our delta H of vaporization, say we could look it up for water, we could then, and we know the normal boiling point of water, we could calculate what the vapor pressure of water would be at 40 degrees Celsius or something like that. So it's a very useful expression. And then the last phase transition is sublimation. We're going to go through this very quickly because basically the same assumptions apply to gas versus solid. The volume of the gas is very large. The vapor pressure above a sublimation is very small, so it's going to be ideal. So it all derives to this natural log of P. And here we have, this is the heat of sublimation, not the heat of vaporization, versus 1 over T. If we have natural log of P or vapor pressure versus 1 over T data for a particular sublimation, we can also derive this enthalpy of sublimation. So those are the 3 phase transitions that we can look at and the expressions we've derived to evaluate the pressure dependence and the temperature dependence of, say, vapor pressures over liquids and solids, or the pressure and temperature dependence of melting. So until next time.